Electrical circuits in houses. The electrical system in a house consists of various types of electrical circuits. An electrical circuit is a closed path for current, allowing it to flow freely to do its job in a load. The circuit contains power source, conductors, and a load. Current flows in a circuit when there is a potential difference across the power source and the current loop is closed. The current flows from high potential to low potential. As the current flows through the load, it does its work. In a DC, direct current, circuit, current flows in only one direction. In an AC, alternating current, circuit, current changes direction. With its frequency, 60 Hz in the US. When the voltage increases from 0 to a positive peak and back to 0, current flows in one direction. And when, after reaching 0, it goes to a negative peak and back to 0, current flows in the opposite direction. One full cycle is completed 60 times per second, frequency, or 120 times per second the direction of current flow changes. In a circuit with a resistive load, the voltage and current are in phase. In a capacitive circuit, with a capacitor, the current leads the voltage. And in an inductive circuit, with a coil, the voltage leads the current. All circuits powering a house are AC circuits. All requirements for electrical installations in the houses are contained in the NEC, National Electrical Code. Typical most common electrical circuit in a house, containing receptacles and light outlets. Electrical panel is a power source for all circuits around the house. How the electrical panel board, is powering the circuits in the house. The electrical panels that distribute electricity throughout the circuits in the houses are connected to a transformer located outside the home, usually a transformer mounted on a pole. Sketch of the electrical panel power supply from a transformer located outside the house with a service disconnect located outside the building. A transformer mounted on a pole or other place outside the house. The electrical panel board that distributes electricity in the house. The service entrance conductors, cable, from the transformer, supplying power to the electrical panel, passes through the electricity meter, and disconnecting device, if installed outside the building. The disconnecting device installed outside the building is most often a circuit breaker that also meets the requirements for emergency disconnect requirement for 1 and 2 family dwellings, and overcurrent protection for the panel board. The service disconnecting device must be installed in an easily accessible location, either outdoors or indoors, but not in a bathroom. Must disconnect all ungrounded conductors, and must be marked as a service disconnect. The panel board must be protected by an overcurrent device on the supply side. For 1 and 2 family dwellings, an emergency disconnect device must be installed outdoors, which device may also be a disconnect device for the service entrance conductors. And overcurrent protection for feeder cable and the panel board. Service disconnect devices must be grounded and bonded. The service entrance cable must be sized to supply the load in accordance with Article 220, 230, and 310 of the 2023 NEC, which means that the service cable may be sized for the primary overcurrent protection rating if the cable is routed to only one overcurrent device. Both ungrounded, hot service conductors may be the same color and do not require special identification. But the grounded conductor, neutral, must be identified in white or gray. The equipment grounding conductor can be bare or insulated in green color of insulation or green with yellow stripes. If a service disconnect is not installed outside the building, between electric meter and the panel board, the main circuit breaker which is installed in the panel board provides a means of disconnecting and panel board overcurrent protection. All grounding and bonding must be made at the service disconnect, which means in this main panel board, grounded conductor cannot be connected to the equipment grounding conductor on the load side of the service disconnect. Main bonding jumper, bonding screw, connecting the equipment grounding conductor and the service disconnect enclosure to the grounded conductor, neutral, within the service disconnect enclosure. Connection of the transformer leads, service drop, to the service cable. Grounded, neutral conductor, wire. Ungrounded, hot conductors, wires. Connection inside the electric meter pan. Neutral wires from line and load side of the service entrance conductors, cable, are connected together and bonded to the meter enclosure. Hot wires of the service entrance conductors, cable, from the transformer side, are connected to the line side of the electric meter socket. Hot wires of the service entrance conductors, cable, to the service disconnect, are connected to the load side of the electric meter socket. Connection of an emergency and service disconnect with overcurrent protection, circuit breaker, for the feeder cable and the panel board located outside the building. Circuit breaker as a disconnect and overcurrent protection for feeder cable and the panel board. Neutral wires of the service entrance conductors, cable, from the meter pan, and the feeder cable to the panel board, are connected to the neutral terminal of the disconnect, that is bonded to the disconnect enclosure and grounding terminal of the disconnect. Bonding jumper has been added to provide a better connection between the neutral and ground terminals. This is not necessary as the neutral terminal is already bonded by a bonding screw. Hot wires of the service entrance conductors, cable, are connected to the hot terminals of the disconnect in any order. Hot wires of the feeder conductors, cable, to the panel board, are connected to the hot terminals of the circuit breaker in any order. The equipment grounding conductor, ground wire, of the feeder cable to the panel board, are connected to the ground neutral terminal of the disconnect as these terminals are bonded together and also they are bonded to the disconnect enclosure. Also, a bonding to the water meter and to the ground rods are provided from this disconnect as required by Article 250 Part 3 of the 2023 NEC. Connection of the panel board. The neutral wire, white, of the feeder cable from the service disconnect is connected to the neutral bar terminal. The ground wire, bare, of the feeder cable from the service disconnect is connected to the ground bar terminal. The hot wires of the feeder cable from the service disconnect are connected to the hot busbar terminals of the panel board in any order. Neutral bonding bridge connects the neutral bars together, but the neutral bars are not bonded to the grounding bars and the panel board enclosure. Neutral conductors of the circuits must be separated from ground conductors in all panel boards and on the load side of the service disconnect. Sketch of the electrical panel power supply from a transformer located outside the house with a service disconnect located inside the panel board. If there is no service disconnect between the electric meter and the panel board, and the main circuit breaker in the panel board is also a service disconnect, the panel board shall be connected as follows: neutral, grounded conductor of the service entrance conductors or cable from the electric meter must be connected to the neutral ground bar of the panel board. Hot, ungrounded conductors of the service entrance conductors or cable from the electric meter must be connected to the terminals of the panel board main circuit breaker in any order. The neutral bar must be bonded to the panel board enclosure and the ground bars, if present, using main bonding jumper, green screw, provided or other approved means. Neutral bonding bridge connects the neutral bars together, which are bonded the panel board enclosure, as required by the NEC. The main circuit breaker is directly attached to the hot buses of the panel board. Also, bonding to the water meter and to the ground rods are provided from this panel board as required by Article 250 Part 3 of the 2023 NEC. The panel board acts as a power source for the branch circuits because voltage is present in it but no current flows. Voltage present on the hot bus bars of the panel board. When the branch circuit with the load is connected and the current path is closed, current will flow. How does current flow from the transformer feeding the panel board to the branch circuit load? Wiring sketch from a transformer outside the building, on a pole, feeding the 120 volts branch circuit installed from the panel board. Transformer has two coils, windings, and a core. The primary coil of the transformer is connected to the medium voltage supply, while the secondary coil of the transformer supplies current to the panel board. The center of the transformer secondary coil is bonded, connected to the earth, grounded, and to the neutral, grounded, wire of the electrical system, which is also connected to the earth. Secondary coil of the transformer has 3 wires. 2 hot wires. And a wire taken from the center of the secondary coil, which is grounded and acts now as the neutral wire. The voltage across the transformer is 120 volts between the ground, neutral, wire and one of the 2 ends of the hot wires, legs of the transformer secondary coil, and 240 volts between the 2 ends of the hot wires, legs of the transformer secondary coil. Sine wave of the voltage on the secondary coil of the transformer. Sine wave of the phase A. Sine wave of the phase B. The voltage, 120 volts, between the common wire, neutral, and the end of each hot wire transformer secondary coil of the transformer is 180 degrees out of the phase. Because the 2 hot legs, 240 volts, are 180 degrees out of phase. The 120 volts voltage drawn from opposite ends of the transformer secondary coil causes the voltages between the neutral wire and the legs to be almost perfectly opposite, which balances the return current flowing in the neutral wire on the return to the power source. Balanced 120 volts from opposite phase and 240 volts between phases. The power from this type of transformer is not true 2-phase power and is called split single-phase power. Split single-phase transformer mounted on a pole feeding the panel board. Primary coil of the transformer is connected to the phase wire of the medium voltage supply and to the neutral wire of the distribution system. 2 hot ends of the secondary coil are connected to the hot service drop conductors. Center of the secondary coil of the transformer is bonded to the neutral of the distribution system and to the conductor. Connected the pole ground rod. The service entrance conductors, or cable, contains 2 hot conductors and the neutral conductor, which are connected to the service drop conductors at the service point on the building. The service entrance conductors, or cable, go through the electric meter to the emergency service disconnect, which is usually also the service disconnect and overcurrent protection for the feeder cable and the panel board. Service entrance conductors terminate at this service disconnect, and the feeder cable is installed from this disconnect to the panel board. When there is no any disconnect switch installed before the panel board, and the panel board contains the service disconnect with the overcurrent protection for the panel board. The service entrance conductors, or a cable, terminate at the panel board. All grounding and bonding required by the NEC must be done at location where the service disconnect exists. Voltage in the panel board: 120 volts between the neutral terminal and any of 2 hot busbar terminals. 240 volts between the 2 hot busbar terminals. 120 volts also exists between the ground terminal, when separated in subpanels, and any hot busbar terminal. because they are bonded together at the service disconnect. The panel board bus bars are designed in such a way that the circuit breakers installed side by side in a row on one side or the other, from top to bottom, are connected to different phase legs of the service entrance cable. Phase leg A, phase leg B. Circuit breakers in the same horizontal row are on the same phase of the service entrance conductors. Since no branch circuit with a load is connected to the panel board, or the breaker or switch is turned off, the voltage is present on the hot bus bars of the panel board, but no current flows from the transformer. When a circuit breaker or switch is turned on, and the current path through the load is closed, current begins to flow. How current flows from a transformer? Through a connected 120 volts load. Sketch of the current path from the panel board power transformer to the 120 volts branch circuit load. When the service disconnect, branch circuit breaker, and any other switch, if installed, is turned on, current flows as follows. From the transformer hot leg, phase, on which the branch circuit is installed, through the electric meter, service disconnect, branch circuit breaker, to the load, through that load, and return through the neutral wire, back to the transformer. When a sine wave goes from 0 to a positive peak and returns to 0, current flows from the transformer hot phase wire through the load and back through the neutral wire to the transformer power source, because there is a potential difference between the 2 points of the circuit. When the sine wave crosses back through 0 and starts to peak negative and then returns to 0, current will flow in the reverse direction. From the transformer neutral point, grounded coil center, wire, through the load, and back through the hot phase wire to the transformer power source. When a new cycle of the sine wave begins, the current changes direction again and changes it each time it passes through the 0 point. A grounded neutral wire closes the path for current flow and keeps this wire at a very low voltage, which provides a stable reference point for the circuit, for measurements and comparisons. It is assumed that current always flows from the hot transformer wire to the load and returns through the neutral, grounded, wire to the power source, transformer. Sketch of the current path from the panel board power transformer to the 240 volts branch circuit load. When the service disconnect, branch circuit breaker, and any other switch, if installed, is turned on, current flows as follows. From the transformer hot leg, phase, through the electric meter, service disconnect, branch circuit breaker, to the load, through that load, and return through the other hot leg, phase, back to the transformer. The transformer phases are 180 degrees out of phase. When a sine wave phase A goes from 0 to a positive peak and returns to 0, current flows from the hot phase A wire through the load and back through the other hot leg phase B wire to the transformer, power source. Because there is a potential difference between the 2 points of the circuit, as the phases are 180 degrees out of phase. When one phase with a positive voltage pushes current, electrons, at the same time the other phase has a negative voltage, which voltage pulls current, electrons. When the sine wave crosses back through zero and starts to peak negative and then returns to zero, current will flow in the reverse direction from the hot leg, phase B, wire, through the load, and back through the hot leg, phase A, wire, to the transformer, power source. It is possible because the hot legs, phase A and phase B, wires, are 180 degrees out of phase. So while one of them acts as the supply wire, the other at the same time acts as the return wire, creating a closed circuit. As a result, there will be a potential of 240 volts between the legs, phases. If two hot wires from the transformer are somehow in phase, both voltages from the same phase will reach their voltage peaks simultaneously, and therefore there will be no potential difference between them and consequently no current flow between them. The voltage will be present in all hot wires, but there will be no current flow. There will still be 120 volts between any hot leg wire and the ground, with the same phase and frequency, but the different voltage peak. The sum of the waveform voltages will result in a much higher voltage, sum of both voltages, which may damage the connected equipment and circuit. In the circuit, with the voltage between the phase conductor and the grounded conductor, 120 volts. If the circuit conductors are disconnected at any point between the phase conductor of the transformer and the ground point of the middle of the transformer, the conductor on the phase conductor side of the transformer will always be live, and the conductor on the grounded middle side of the transformer will be dead with respect to ground. Unlike in the circuit, with the voltage between the phase conductors, 240 volts, where between the two disconnected phase conductors from either end of the transformer there will always be a voltage of one or the other phase with respect to ground. For electric current to flow, a closed circuit is necessary that includes a power source, conductors, and a load. In homes, a closed circuit in which electricity can easily flow includes a panel board as the power source, cables or raceways with conductors as conductors, and a load, which depends on what the electricity will be used for. A branch circuit is a part of an electrical system installed from the final overcurrent protection device, circuit breaker, which in homes is located in the panel board, to the electrical outlet that supplies the load. Circuit breakers, final overcurrent protection, in the panel board. An outlet that can be an receptacle outlet, a lighting outlet, and an appliance or other electrical device outlet. A switch is not an outlet, because an outlet is a connection point for electrical devices. Two types of electrical branch circuits are installed in homes. Lighting circuits that power receptacles, light outlets, or both with a voltage of 120 volts, and dedicated circuits that power specific electrical devices and appliances with a voltage of 120 volts or 240 volts. All electrical circuits are described by Ohm's and Kirchhoff's laws. Sketch of a branch circuit with a 120 volts load. Sketch of a branch circuit with a 240 volts load. The branch circuit must have the ampacity to deliver power to the load so that it can operate efficiently and not cause damage to the circuit. The ampacity of the circuit is determined by the load connected, and the minimum size of the conductors shall be sized for the ampacity not less than the non-continuous load plus 125% of continuous load, and so that the ampacity of that circuit is not less than the maximum load to be served, after taking into account any adjustment factors, number of conductors, length, etc. Continuous load occurs when the load can operate at maximum current for 3 hours or more. If less than 3 hours of continuous maximum current flow through the load, the ampacity of the circuit must be 100% of the maximum current flow through the load. If 3 or more hours of continuous maximum current flow through the load, the ampacity of the circuit must be 125% of the maximum current flow through the load. The branch circuit ampacity with mixed loads connected must be calculated as a sum of non-continuous load at 100% plus continuous load at the 125% after any adjustment factors applied before the calculation. The minimum size of copper conductors in installations rated up to 2000 volts must be 14 gauge. In homes, most branch circuits are 15 or 20 amps and have copper conductors, usually inside the cables since the cables are commonly used. The minimum copper wire size for a branch circuit is given in Table 210.24.1 of the 2023 NEC, which states that for a 15 amps branch circuit, 14 gauge wires, conductors, must be used. And for a 20 amps branch circuit, 12 gauge wires must be used. 15 or 20 amps branch circuits are used to power lighting outlets, receptacles and lights, and small household appliances. Another type of copper conductor circuits found in the same Table 210.24.1 of the 2023 NEC are those dedicated for household appliances and are 30 amps branch circuit with 10 gauge conductor size, 40 amps branch circuit with 8 gauge conductor size, and 50 amps branch circuit with 6 gauge conductor size. If the circuit is determined by the ampacity of the conductors, the connected load must not be greater than the ampacity of the circuit for non-continuous load, and when the load is continuous, the connected load cannot be greater than 80% of the ampacity of the circuit. When the circuit is determined by the load to be connected, the circuit must be sized at 100%. When the load is non-continuous, and at 125%. When it is continuous. Branch circuits supplying household cooking appliances must have rating not less than the maximum load to be served. Each branch circuit must be protected by an overcurrent device, circuit breaker. A branch circuit overcurrent device, circuit breaker, must be located at the point where the branch circuit receives voltage, usually panel board. and must be installed in each ungrounded conductor. An overcurrent device must be connected in series to each ungrounded conductor. Circuit breaker must open all ungrounded conductors automatically and manually. All conductors must be protected against overload, which is also accomplished by a circuit breaker. The overcurrent device, circuit breaker, must be sized in accordance with NEC requirements, which depend on the ampacity of the cable conductor and the connected load. An overcurrent device automatically interrupts the flow of excessive current that can damage a branch circuit. Circuit breakers have a standard rating that must be selected from Table 240.6a of the 2023 NEC and rounded up. For small-sized conductors, overcurrent protection after adding the correction factors required by the NEC shall not exceed, except for specific installations, like a motor loads, etc. For copper conductors, 14 gauge 15 amps, 12 gauge 20 amps, 10 gauge 30 amps. The overcurrent device, circuit breaker, can also provide arc fault protection and ground fault protection for personnel. If a receptacle is connected to a branch circuit supplying more than 2 receptacle outlets, the receptacle cannot be less than specified in Table 210.21, B3, of 2023 NEC, which states that for a 15 amps branch circuit, the receptacle must be rated at 15 amps. For a 20 amps circuit, 15 or 20 amps. For a 30 amps circuit, 30 amps. For a 40 amps circuit, 40 or 50 amps. And for a 50 amps circuit, 50 amps. Dedicated branch circuit can supply the only load for which it is rated, and the load cannot exceed the branch circuit rating. Where a single receptacle is connected to a dedicated branch circuit, the receptacle must be rated not less than the branch circuit rating. All wires, conductors, of the same circuit must be contained in the same raceway. This also applies to cables. The AC, alternating current, system must be grounded. All electrically conductive materials containing electrical conductors or equipment that are not current carrying under normal condition must be connected to earth to limit the voltage to ground of those materials. Each branch circuit in homes contains 2 current carrying conductors and an equipment grounding conductor. 120 volts branch circuit contains 2 current carrying conductors, one of which is intentionally grounded and is called the grounded or neutral conductor. Hot phase conductor wire supplies current from the panel board, while the grounded neutral conductor wire provides the return path for this current. The National Electrical Code does not specify the color of the insulation of a hot wire. The most common color for the insulation of a hot wire is black. Red is also often used for a secondary hot wire, and in multi-wire installations blue and brown are also used. Grounded conductor, neutral, must be identified, which specifies white and gray colors for it. In a 240 volts branch circuit, the 2 wires carrying current are usually distinguished by the colors black and red, but very often they are the same black color. The equipment grounding conductor may be bare or insulated and colored green or green with yellow stripes, and this conductor cannot be used as a grounded, neutral, or ungrounded, hot conductor. Equipment grounding conductor is a conductive path for ground fault current that is not a current-carrying conductor under normal conditions. A multi-wire branch circuit is a circuit in which the hot wires share, use, The same neutral wire. Multi-wire branch circuit can power only line to neutral loads. But exception in same article states that this kind of circuit can power also line-to-line loads when it powers only one utilization equipment. And all ungrounded conductors are opened simultaneously by overcurrent device of the branch circuit. All conductors of multi-wire branch circuit must originates from equipment containing an overcurrent device for it, and have a disconnect which simultaneously disconnects all ungrounded conductors in place where the circuit begins. The disconnect must also disconnect all ungrounded conductors in place when the multiple branch circuit originates. If two or more circuits supply device or equipment on the same mounting strap or yoke. In the vast majority of homes, all types of cables are used for branch circuit installations because of their flexibility, rather than any type of conduit. The cable commonly used for branch circuit installations in homes is NM, non-metallic sheathed cable. All installation requirements for NM cable are presented in Article 334 of the 2023 NEC.